Okay, I would like to welcome Shields. He leads the exploratory data analysis group at the Helmholtz Center of Information Security in Saarbrücken. His lecture today will be on interpretability and causality. So welcome, Shields, and thank you for being here.
Thank you very much, Santiago. Happy to be here. Indeed. So, well, I always like to start with pointing out that everybody mispronounces my name. So don't take this personally, Santiago. I mean, everybody does this, but my name is Vreeken. And indeed, I'm with the CISPA Helmholtz Center for Information Security. I'm also affiliated with the Max Planck Institute for Informatics. And I'm also a professor for computer science at Saarland University. And my research, and hence also my lectures, they always revolve around, okay, what can we learn from data? And I say we, and not so much what can machines learn from data. Let me actually start sharing my screen up. So what can we learn from data? I mean, it's great that machines can learn from data, that they can extract all sorts of nice dependencies that we may be able to use to predict certain things. But in the end, I find it really important that we as humans also get something out of this, and so that we can build better theories about how the world works, or perhaps even get closer to the grand theory of it all. I guess it was roughly half a year ago that I was asked to give this lecture, and I happily said yes, because this is a topic that I like very much. In general, I've been using data and AI for material science. I mean, I've been working with the people from the Fitzhaber Institute now for quite a few years, as well as the topic they specifically asked me to lecture about, namely interpretability and causality, given that these are smack in the middle of my research interests. Now, when I said yes to this request, I thought that, I mean, well, one lecture, sure, I can do both. And then I started thinking that, well, wait a second, I mean, you in the audience, I mean, although the curriculum for this course looks fantastic, you know nothing of the stuff that I want to talk about. I mean, so I had to make a choice. I mean, I had to make a choice of either staying very high level and not going at any depth and any detail of either interpretability or causality, or, well, make a choice and go for one of the two. And that is essentially what I did. So I'm going to be talking today mostly about causality, with the intention that it gives us interpretable models. And I'll try to point out why causality is here let's say the first-class citizen, and from which interpretability then follows. So the questions of the day that I would like to cover with you are, first and foremost, what on earth is causation? I mean, we all have a certain intuition about it, but can we make this formal and not all too hand-wavy? Now, if we have such a thing, such a definition, I mean, is it possible to determine causation? I mean, can we do this via experiments? If we don't have specific experiments, we just have data, is it possible to get a fingernail behind if something causes something else? And well, if that is then possible, I mean, how, given some data, can we discover the causal dependencies from it, such that, well, either we obtain more robust machine learning algorithms that make decisions on the right grounds, or we, as humans, can actually learn something, but hey, wait a second, given the data, the causal structure of this problem seems to be like this, and we thought that X was only caused by that, but maybe this is also, hey, wait a second, let's run some experiments, and so on and so forth. We'll get there once we get there. Let's first take a look at the first question. What is causation? And then I always like to grab a random, typically online dictionary and just see, okay, what do they say? I mean, can I use this as a starting point? If we do this for causation and we look in the Merriam-Webster dictionary, then it says something that, well, doesn't really bring us further. I mean, the relationship between something that happens or exists and the thing that causes it. It's a bit circular, right? I mean, that's what on earth are we going to be able to do here? Dictionaries are of no help. And even if you dig deeper into the literature, so let's say philosophy or whatnot, I mean, there's lots of things that have been said about causation. You're not going to learn much either, because it turns out there is, well, what I'd like to say, a godzillion different definitions of what is causation, what is a cause, what is an effect in very specific circumstances, and none of them really capture the true gist of it. In the last 2 decades, 3 decades, perhaps, if we're a bit more generous, there have been some major advances from the theory side in computer science in particular that actually do, I think, hit the nail on the head. Let me walk you through that in this lecture. So what we want is, in the end, given some data over some attributes, some things that we measured, right? Here I just called them X, Y, well, up to Z, I mean that. And ideally we would like to get some kind of diagram like this, which is very easy to read, namely X causes Y, that's why there's an arrow from X to Y. Y and Q together cause T, that's why there's arrows, and so on and so forth. So that would mean, just by this DAG representation, that if we were to fiddle with the value of X, that, well, that would have an effect on the value of Y, which would in turn have an effect on the value of T, but not on the value of Q, because there's no path from T back to Q. All this downstream. It's an acyclic graph. Whether you can debate whether humans have diagrams like this or some version of it in their minds when they think about causation, about changing systems. Some people do believe this, other people strictly don't believe this. Some people think it's something way more complicated. That's a debate I don't want to go into. For now, this is the abstraction. What is our goal? Given some data, can we get a diagram like this? Okay, well, then we first still need to know what is this definition of causation. And that, so I went from a dictionary definition to a very intuitive one if we fiddle with data, but not really satisfying yet. Now, why did I start with these definitions and pointing out that this is difficult? And why did I mention that, well, while you are very smart and know a lot, you also know nothing about this topic, or unless you've taken a course coincidentally at causation, which they're still very rare and well, far and few between. Causation is, I think, really the foundational bedrock of statistics. And sadly, it's not being taught as such because of this lack of understanding. I mean, that's, in fact, in statistics, people shied away from causation for well, over a century because they couldn't really put their finger on it. What we do in statistics and hence in machine learning, big data, AI, and all that good stuff, we typically focus only on correlations or associations or dependencies. And those are, well, let's say, misleading. I mean, that's often at best. So, for example, here, if you look at the data between over a number of countries, over here, and we look at, okay, how many storks are actually nesting in these countries, and what is the birth rate in these countries, there is a significantly strong dependency between storks and birth rate, which, well, perhaps the theory of stork is correct after all, right? It's the storks that deliver the babies. And if we want to increase the birth rate here in Europe, right, I mean, not to sort of get the age distribution a bit more flat rather than too skewed, perhaps we should massively invest in storks. Well, we all know that this is not true, right? I mean, that's and this is just as an example. Correlation does not tell us anything about causality and what is actually going on here. This is why I also include the area of these countries. The larger the countries, typically the larger the areas where storks can nest freely without disturbance from humans, and hence you have many stork pairs. Typically also countries with a relatively low economic development, and lower economic development correlates very strongly, or causes perhaps even the birth rate, because people don't have to work like both family-wise and so on and so forth. So there's something else going on rather than a direct causation between storks and birth rate here. So rather, we should talk about dependence. I mean, these attributes are clearly dependent in some way, right? I mean, so they are nodes in this diagram that I showed earlier, where somehow there are some edges incoming from some central source, and well, that is actually causing everything here. Another example, I mean, that's just to distinguish causation and dependence. I mean, why these are really different things. I mean, let's go to a snapshot from our online favorite or not, I don't know. I mean, online retailer, I mean, Amazon, who, if you buy something or click around, I mean, they always suggest, I mean, well, combinations of products. I mean, they typically call this better together. Obviously, this is for Amazon, right? Not necessarily for you. And here is an example that I love, because well, here clearly it shows that the mechanism that they're using is just association and has nothing to do with causation. This is a snapshot from a few years back. In the meantime, the systems got improved, and let's say the worst bugs got squashed. But still, the mechanism behind it is not causal. What do we see here? Is that, yeah, I mean, obviously, if you buy a laptop, I mean, well, perhaps it's also time for a new backpack, right? So that would be the, let's say, the arrow of time in the causal direction. But if many people buy a new laptop, also buy a new backpack, then for the system, this is just, I mean, a symmetric dependency. So why not suggest a new backpack, right? I mean, that's, or a new laptop for people who buy a new backpack. Yeah, because I mean, if you spend $48, I mean, why not spend $900 instead, right? I mean, does not make any sense, but yeah, we're getting the causal direction here wrong. Okay, so let's now go into why causality has been neglected in statistics for so long, and why it is so difficult to determine it from data. I mean, that's even though we humans have a very strong intuitive sense for what is causal, what is not. I mean, you could say that our brains are causal mechanisms. We live in a causal world. We have to make do with it. For that, let's go to some probability theory. So the naive approach, right? Intuitively, this kind of feels right in that. So if we have some attribute cause, and that cause is some attribute effect, right? Then somehow it feels that the probability of cause times the probability of effect given cause should somehow be higher than the other way around, right? It's the more natural direction in that. So if we were to see this, that probability of cause and probability of effect given cause is higher than the other way around, then well, it should be safe to conclude that cause causes effect in that. Sadly, this fails because both these quantities are equal. They're just simply factorizations of the same joint distribution of cause and effect together. Well, that's kind of a pity, right? I mean, that, so this doesn't work. And that already illustrates why in statistics, where essentially everything in probability theory is always expressed in marginal probabilities, such as P of effect, and conditional probabilities, cause given effect, this language fails, right? The language fails. This is the important part. Okay, let's say, okay, well, if this is now symmetric, screw it, we're just going to make it unsymmetric, right? I mean, that's you can't catch me that easily, because, well, why wouldn't then the probability of effect given cause? That should be higher. I mean, cause should elevate this probability of effect. That should be higher than the probability of cause given effect. Could be one suggestion that you have. That's well, sorry, that also fails. I mean, that's even though in specific instances it may hold true, and you may determine the correct direction. In many others, it will completely botch, because what you're actually measuring here depends completely on what is the distribution of effect, given cause given effect, what are the domain sizes of these things, and so on and so forth. All sorts of things that have nothing to do with the actual causal effect. You can play this game a number of times more. I'm not going to go into that because all of them in the end fail. There is one gold standard accepted way to determine cause and effect in statistics. I mean, this already goes down all the way to Robert Fisher, I mean, in the early 1900s. And the ultimate test is that of a randomized controlled trial. It's the de facto standard. So what the idea is, we have some postulated cause X, and we have then a postulated effect Y. We want to see, does X cause Y or not? And if so, how strongly? So what we do is that typically we take X to be discrete valued, nominal, such that we can consider it treatments. You get the green pill or the blue pill or something like that. And then we want to see, okay, does this, taking this pill, so let's say a placebo and an actual treatment, does this have a positive effect? I mean, that's, are you shielded or more shielded from catching corona or something like that? There's also obviously a number of other variables that might be important, or that we know that are important. And those we call the covariates, and we call them Z. I mean, this can be multiple things. Now, ideally, we gather a very large population of test subjects in that. So in this case, let's say we want to test whether corona works, right? I mean, large population, hundreds of millions of people. I mean, that, and what we do, we randomly split this into two, ideally equi-sized groups, A and B. And we don't do this completely at random. I mean, that's one way how you can do it. But ideally, we want to make sure that the covariates that we think may be of influence, we want to make sure that in group A and group B, that on Z, these are as equal as possible. So for example, we don't want to have randomly group A much younger than group B, and then see, okay, yeah, well, the vaccine works much better in group A. Yeah, maybe actually it doesn't, but it's just due to age, right? I mean, so age would be a good thing to put in your covariates. Same thing, sex. I mean, maybe it works better or worse for men or for women. And it's all possible. Okay, let's make sure that those things we flatten out, and we make sure that we really see through that mess. Okay, so that's why we want to distribute it randomly, but also controlling it to somewhat. Now then, to one group, we give the treatment, And the other one, we give the placebo or the other treatment. And of course, we can have as many groups as we like. We just have to gather more and more stress subjects. And then in the end, well, we run the study. Well, so we give these people these pills, or we force them to take these pills. And after some amount of time, we see, okay, well, we're going to measure why, right? I mean, that's how many people did catch corona or not. Okay, good. Then what we can do, we can start to see, okay, R, Y, so the effect that we see, and X, whether what color of pill did you get, are they dependent or not? And if it turns out that they are dependent, so we write this as this, and so without the strike through, this means independent, with the strike through, it means dependent. I don't know if you already caught this in earlier classes, but I'll use this symbol a number of times throughout, so it's always good to re-explain if necessary. So if Y and X are dependent, well, then in this particular case, given that is X is the one that we instrumented, that we changed, right, that we intervened on, and that is the only sensible explanation for the effect of Y, because the covariates are all taken care of. They were excluded from the equation, so to speak. X causes Y. Okay, this is beautiful in that sense. Well, it is ultimate, and even the statisticians accepted this back in the day. But it's not really ideal in that. So gathering a large population and well, exposing them to some experimental treatment, yeah, this is sometimes unethical or difficult, right? To gather volunteers for something. Unethical, for example, if you want to prove that smoking causes lung cancer, you could use a randomized controlled trial, but yeah, okay, do you really want to force a large population to smoke for a large number of years when your hypothesis that it causes cancer? I mean, that is a bit icky, right, to say the least. Another problem is that you need large populations, otherwise you don't have any statistical power. You can't draw any strong conclusions. And controlling for Z, so these covariates that we don't want to influence or mock up our result, those are very difficult to control, because maybe we now have, let's say, a younger female, and it goes to group A, and here we have a younger male that goes to group B, and then, well, okay, do we now, so they're equal on age, right, distributed, but now not on sex, and well, the more covariates you have, the more difficult it becomes to control, exponentially so. So that's kind of horrible. Good. Let's continue. I mean, that's so. This is the accepted gold standard, and I already said that in just standard probability theory, marginal conditional probabilities, they don't identify causation, but this does, right? I mean, it makes sense. I mean, whether you know this is an RCT or an A/B test or other names, that doesn't matter. You've heard about this. So what happened? What happened? I mean, what is the magic, right? Well, the magic is this. The standard things that you know about probability theory, these are notions from, no, these are observational notions. Essentially, we have some data, and in that data, we count. And this gives us an empirical estimate of the distribution of these values, be it conditional or marginal. But, the idea is that, I mean, if we would have infinite amounts of data, then we don't have an empirical, but we have the population estimate of this distribution. But still, it's just observational. I mean, we were not intervening into the system. It is just the distribution of Y, in this case, given that we observe variable X to take a certain value, and that is that, right? I mean, that's, there's nothing special about this. This is what we do in everyday machine learning life, statistic life, data mining life, and whatnot. It's also what we use all the time when we do regression or classification. But, because the beauty is that these conditional distributions through Bayes' rule, we can determine very straightforwardly. So if we have data, observational data that we just gathered over the joint, so Pxy, and we can also determine what is the distribution of P of X, right? How often did we see X? That actually gives us directly the probability of Y given X. Beautiful, right? I mean, that's, and hence we've been using this all along. And that's, now, this is something different than what we did in this randomized controlled trial. We can't express that truly in conditional probabilities, because actually what we're doing, and this is a notion that was only posited, not as my slides say here in 82, but much later. Actually, what we have our hands on is an interventional distribution. And in the interventional distribution, you write as such. This is now the distribution of Y, given that we do not just observe that X coincidentally or through whatever reason took a certain value, right? I mean, that's, but we actually actively set this variable to be that value. We basically force people's mouth open and put the pill in, so to speak, right? And that's whereas in the above one, we just say, okay, well, how well do people do that took, let's say, aspirin? But yeah, some people take aspirin because they just they like it, they like the taste, they like bitter. Other people they take it because it's prescribed. That is observational. In interventional, we would only give aspirin to people with a headache, right? And that's and only under these conditions. Another group of people who also have a headache, we don't give aspirin. And now we can see, okay, did giving the aspirin, did this actually bring down the headache-ness, right? The probability of a headache. So this is a very subtle but very fundamental difference between a conditional distribution, as you know, and interventional. It's really like taking the action, right? And not just passively observing, but really like we force this and then we see what happens, right? So it's sort of the and then what is baked into this. So it's the distribution why if we would observe, if we would intervene by artificially forcing it to take a certain process, and then how it plays out. Now, that is coincidentally the same thing as we get through a randomized controlled trial, right? And that's what we do in a randomized controlled trial is see if the distribution, let me just go back a slide, oops, here. So if this y and x are dependent or not. Actually, what we do is we compare the two distributions, the two interventional distributions. And if those interventional distributions are unequal, okay, well then by actively intervening, we really change something in y. It's the only explanation. Okay, good. Now, essentially this means that although in statistics we did not have the language to express this interventional distribution, we kind of already had intuitively the notion, right? And that's so the only accepted way to tell causation from just association already used this interventional do calculus type definition, even though we didn't have the language for it. That only came in the 80s and early 90s. Perhaps you're convinced, perhaps not. Let me give you an example. So let me talk about one of my favorite topics, namely coffee. And that, without coffee, I mean, I would not be able to give this lecture. And that, I slept like crap, but coffee keeps me going. So here's a picture of my coffee machine. Very nice Italian piece of engineering. I mean, I like German cars, but espresso machines, I prefer the Italian ones. And it's also a perfect vehicle, so to speak, to explain what is now the interventional distribution. In an espresso machine, you have a boiler, right? The boiler needs to be brought at a certain temperature, and then you get a certain pressure, right? I mean, that's a sort of pump, and then push it then through the ground beans and on, and you get the good stuff. Now, what you also have are these dials that tell you, okay, what is the temperature and what is the pressure? That's very important because, well, if the temperature is not right yet or the pressure is too low, you're not going to get good coffee. So you need these measurement devices. Now, suppose that Y is the actual pressure in the boiler, right? What is actually going on. And X is the pressure measured here by this front gauge, typically here the right one, at least for my machine. So this barometer, manometer, whatever you want to call it, I mean, this gauge, if it's a good one, and well, Italians being espresso lovers, I mean, they make sure that their pressure meters are really good. Well, that should be very close to the actual pressure in the tank, right? And that is very good for my exposition here, because if this barometer works well, the conditional distribution of the actual pressure in the tank given the observed measured pressure, well, that's going to be unimodal. So it's basically going to be a distribution just around the actual value of X, right? But basically it should be pretty much one-to-one, perhaps with a bit of noise, right? Because I mean, just like German cars now and then break down, also Italian coffee machines may not be perfect all the way, right? I mean, it happens. But essentially, it's just going to be the same value as X. That is the distribution. Okay, good. Now, let's play a small thought experiment. I mean, suppose I'm going to intervene on the gauge, on the barometer. And I'm going to take off the glass and I'm going to move the needle to the left or to the right. And well, obviously, I mean, it's not going to have any effect, right? I mean, that's you and me both know this because we know how these things work. So what does it now mean in the do calculus, in the interventional distribution definition? That actually means that because we can do this experiment, it's meaningless, but the interventional distribution of y, if I do move this hand of the meter around, it's just not going to do anything. So this interventional distribution will be actually the same thing as the marginal distribution of y. Okay, well, this is interesting because if the marginal distribution is now the same as the interventional distribution, the intervention didn't have any effect. So wait a second, that means that we have another tool to determine cause and effect. That is nice. Also the other way around, suppose that I would now have, I don't know, a hand pump and I connect it to the boiler and well, I now look at the interventional distribution of X, the actual pressure in the pump, in the boiler, given no, wait a second. I look at the pressure depicted on the meter, intervening on the pressure in the boiler, right, by pumping very fiercely in that, then obviously I'm going to see an effect, right? So the distribution of the hand positions is affected by the pressure in the tank. So it's not the marginal distribution of X. So there's a discrepancy there. Okay, yet another tool. Okay, good. So I hope that this now illustrated a little bit, so in a gentle way, that there is really truly a difference between these conditional and interventional distributions. And this is really fundamental. And we're right now, I mean, all of you are, well, somewhat lucky now that you get this. I mean, but most of us are very unlucky that, I mean, all our statistics classes always started from conditional distributions and not from these interventional ones. And I really believe that this is a revolution that we're going to see in the next few years. It should be the other way around, because thinking that you can do everything with conditional distributions is currently breaking quite many things in machine learning. It's, in the end, you need to think causally. Okay, so let me explain this a little bit before we can have a short break and perhaps some questions. Because these conditional distributions that you know and you love, I mean, they're not all bad. And if they would be, why on earth would we have this course, right? And machine learning and big data AI would not fly at all. Now, the main point is, I mean, what do you want? And if you just want to predict the value of y given the value of x, conditional distributions are great. They're absolutely fine. And that's basically what they're really good at, especially through means like machine learning, deep learning, kernel machines, and well, many other methods, is essentially interpolation. Interpolating y between its cause and effect, it's all fine. I mean, that's so it doesn't really matter. So if you now, I mean, I don't have this on the slide, so I'm just going to do this with my hands. If this is the value, right? So this is now, let's say y, that's my fist here. This is what I want to predict, and actually it is caused by x, right? So it comes here from this side, and this one I measured, and well, y in turn causes this z, right? And suppose that I've now measured both x and z, and I want to predict y. Now, even though z is a downstream factor of y and not causing, I can use it to predict y better than I can just predict it from x. Interpolation is absolutely fine. Extrapolation is where things go wrong. And where do things go wrong? If you really want to say, okay, well, what would happen if I change something? Because obviously, if z is caused by y, then changing z will not change y, right? So if you actually want to act on the x that you identify, so the thing that you want to predict with, if there's sort of a policy intention there, then you don't want to have these conditional distributions. You explicitly want to have these interventional distributions. Sometimes you get lucky. If you set up your experiment right, then this conditional distribution may be equivalent to this interventional distribution. But yeah, then you're counting on luck, and well, everybody needs some luck, right? I mean, without luck, nobody fares well. But in science, we try to eliminate luck as much as we can. And that is something that I will be discussing in the second half, or second third, actually, of the lecture. So, for example, where do you really need this? Well, drug administration, right? Did this drug actually cause something or not? In discovery in general, drug discovery, I mean, in science actually in general, because we're always after, I mean, what are actually the knobs that nature is playing with, rather than just being in complete awe of everything at the same time. Now, from a research perspective, and these are comments where you can see that I took these slides from my own lecture, these conditional Probability stuff, in a way, is very boring because there's so much research about it. There's so many methods there, right, for prediction, for regression, for classification. In a way, it's kind of boring. I mean, that's you're just coloring in smaller and smaller, well, square nanometers by now, but, which may have a significant effect after all, because people may use it, but it's kind of boring. The interventional stuff, this is still very, very new. This is really stuff that only got defined in the 90s properly, and it had quite a long time before it was picked up. But, and you only see in the last decade or so, you start to see more and more methods that are at least aware of these distributions and that really want to tease apart cause and effect. Okay, now, let's see. Let me very quickly look whether it makes sense right now. Yeah, so actually, yes. So are there any questions? Let's have a very short break, 5 minutes or so. And well, or I mean, first do questions and then have a short break. Oops. So feel free to use your, switch on your video or type it in the chat.
Yeah, if nobody goes, I have a question.
You're very welcome to.
This interventional approach, let's say in general, doesn't it require that the descriptor that you use is invertible, in the sense that you operate on the descriptor? So you have your distribution, and yes, and you say, I change something like giving the pill or not.
Yes.
And I observe what happens.
Yes.
Now, if your descriptor is a kind of abstract layer with respect to what is your actual thing that you're observing, and changing the value of the descriptor is not immediately clear how to change your input kind of material. I'm always thinking about materials, of course. That can be a problem if I see it correctly, because I say I can easily change variable x1, but yes, I have no idea how to produce the material. Let me just go out of the abstract.
Yes.
It has x1 different and all the rest equal.
Yes.
So I don't know what is why that has been so right.
Okay, so I don't see the link. So this is, let's say, a clash of languages, right? I mean, the invertibility. Mm-hmm. I see the problem. But invertibility, I don't map one-to-one to what we typically do. So
no, I didn't.
Let me try to.
Yeah, just go on. Yeah, sorry. Yeah.
So let me try to give one example here.
Yes.
So just to let's say re-illustrate, perhaps in surplus, but suppose that we have some molecule, right? I mean, or we have a whole bunch of molecules. I mean, I'm thinking about, let's say, the gold nanoclusters that we've been working on in the past, right? So we have some molecules, and some are let's say more flat than others, right? I mean, so the planarity, I mean, that's is potentially the descriptors, right? I mean, that. Now, suppose that we have a large collection. We generated a large collection of these molecules. Now, what we could look at, what we could simply go through our database and see, okay, what is the, let's say, the free energy of that could be Y, right? I mean, that's something that we want to predict. I mean, I'm just making this up as I go, right? I'm not a material scientist, so what if I say anything stupid, it's all on me.
That's all right. Okay. Yeah, it's
the
idea. Yes, yeah.
But if we just have this large collection of molecules, then we could just simply select those that are flat, right? I mean, that's and then we have free energy. Well, that is something different than taking a random molecule and forcing it to be flat, right? I mean, that's because that might not have been in the database, right? I mean, the molecule might really not want to be there, and so that is the main difference. That is the main difference. That is what you do in this do calculus, right? This interventional distribution is take your favorite molecule and force it in a certain, take out an electron, I mean, squish in another atom, something like that. This is what you can think of, right? I mean, that's. This may be very difficult to access, which is exactly what I'll be lecturing in the next few slides. Okay. But that way, I mean, if you were able to do such an experiment, then you can really determine what is the cause, what is the effect, right? And that, if I can, like by flattening these molecules, right? I mean, if I really see, okay, by actively flattening them, or actively, let's say, I mean, making them more round, right? I mean, that's I see really a difference in the free energy. Okay, then this clearly has an effect, and it's not just some random association that happened, I mean, in our data generation, or it's just how nature likes to have algorithms, molecules in general. So The invertibility was not in my answer, but does this go a little bit in the direction of what you?
Yeah, it goes perfectly in the direction. And actually, let me exploit the example because it makes more clear what I wanted to say. So you partially answered already. Now, in that particular example, we used, say, this coordination number as input to the model, right? So as a feature. So this coordination number is how many neighbor on average each atom sees.
Yeah.
So it's easy to say I changed this number from 3 to 3.5.
Yes.
It's not trivial to construct a cluster that has this change and all the rest is the same. It may even not be possible.
No, okay, but wait a second. So this is a bit different. So this would be the, let's see. Okay, yeah, I see where let's say in the lecture it then went wrong. So in a randomized controlled trial, you would indeed just say, you know what? Okay, I only change this and nothing else, right? And that indeed the molecule may not want this, right? I mean, that's because if I add an electron here, then something behaves there, and if I force that is impossible, we're in a different universe.
Because the features are correlated, yes.
Exactly. That's. However, this was. Let me just quickly go back to the randomized controlled trial slide. Where are you here? So there we are. This is basically what these covariates said. I mean, that's you're in a way, perhaps because I put too much emphasis on it, I mean, you're over focusing on those. These are the covariates that I require to remain the same. And if I say, well, I don't care about any other property, right? I mean, that's I just generate my materials with an additional electron or this coordination number, whatnot, right? And yeah, if then they start to behave differently on Z1, Z3, but I don't care about these Zs, about these other descriptors. All is fine and dandy. All is, because what I do know is that I actively intervened on these X's, right? I mean, that on the adding this electron, whatnot. However, if you do know that, let's say, for example, larger molecules are already, I mean, that they have a larger over a smaller free energy, whatnot, right? I mean, there's already a known link. I mean, that's then, yeah, maybe by adding this electron, actually, you just make it larger, and it's not really adding the electron, it's just a larger molecule that is causing the effect. And then you should, the size of the molecule should be in your covariate. It needs to be controlled. But in practice, already in this RCT, I mean, that's, so when I say it's difficult to control for Z, the more things you want to control, right? If you want to say, okay, I want to see if my COVID vaccine, if it works, right? And I want to control both for age and for sex and for hair length, right? Those two might be confounded. I mean, that's, but maybe let's say for men with longer hair, it works better than with people like us, right? Where the hairline is receding, which would be very unfortunate. Maybe it's the other way around. That would be fortunate for us. I mean, that, well, and so on and so forth, right? Basically in Z, you put all the things that you wonder that might already be affecting the effectiveness and which you want to see through. But if you don't have any such hypotheses, then well, Z can be empty.
Okay.
Specifying what goes into Z, that is very difficult. And this is why these medical trials are, I mean, very expensive in many which ways. Because basically they need to feed in as many things as possible. For us, in practice, and I mean, like for us material scientists, I mean, I'm very inclusive towards myself right now. We don't typically do an RCT. I mean, but for me, this was more a bridge that there exists this interventional distribution. That is basically the bridge, right? There's just one way of accessing it. And once we have the interventional distribution, hey, then we can determine if something is causal or not. Yeah, good. Okay. Yeah, so I don't know what the structure. I mean, I'm happy to continue with the lecture. I mean, not so unless people say no, I don't hear anything. Maybe because you're not here. Maybe because you want me to continue. But now we've established a bit more clearly what is now this interventional and a conditional distribution, or just an observational one. And we've already been discussing. Okay, so how can we get our hands on it? That is exactly what I've been preparing. Not yesterday when I was preparing the slides. And that, the bigger question here is if we cannot directly access this interventional distribution, right? I mean, that's this may be because we are simply too lazy, right? I mean, that's maybe we do not want to spend all these CPU cycles to generate all these molecules or whatnot, right? I mean, that's maybe there's too many factors to control for, I mean, all that stuff. Or like in the smoking example, we ethically, we're not allowed to, right? I mean, we can't force people to smoke. Well, that doesn't mean that this interventional distribution does not exist, right? That's, even though we can't directly access it, it does exist. I mean, that's it's sort of like a mental exercise, and that is, I think, the most important realization. I mean, that needs to sink in, that it exists no matter what, and because it exists, we can reason with it. And actually, this is what humans are doing all the time, even though we didn't have a name for it. And what humans also do all the time is deriving cause and effect, or postulating them, right? I mean, that's updating your working hypothesis on how the world works, right? I mean, that's if I take this pen and I drop it, well, it's gonna, well, if I let it go, it will go down, right? I mean, that's our working hypothesis, even though I'm in Saarbrücken and gravity may work differently here locally than it does in Berlin, who knows? Yeah, but that's our working hypothesis. And if we see evidence to the contrary, then okay, we would have to update our hypothesis. It has to do with Bayesian learning. I don't want to go there, but we're constantly trying to figure out, okay, is our model of the world causally still consistent? Let me explain this visually using some slides from Ferenc Hoxhar, who did this very, very well. And well, let's say copying is the highest form of flattery there, right? So the standard setup in machine learning is like this. There is some process. This process has some observable joint distribution. That means we can observe x1, x2, x3, right? The descriptors, I mean, also the target. I mean, that these are things that we can observe. And from this, this observation, I mean, there exists this conditional distribution, right? What is the free energy giving in all the descriptors or some descriptors that we are of interest? Now, in practice, we don't deal with the entire observable joint. We don't have access to this distribution. We're not going to simulate every possible material, right? I mean, so we have some training data, just the molecules that we did generate. And from this training data, through some means, we get a trained model, right? Which is basically an approximation, a guesstimate of what is basically the value of y given x. And this model has some parameters in theta. And those parameters we want to tweak such that the predictions are as good as possible. This is what we do all the time. This is basically what all of machine learning is about, right? Just this one slide. Very compact, but it's true. Causal learning works slightly differently. Causal learning looks like this, in that there is the observable joint. Just mean, well, if everything just goes as it goes, right? And from this observable joint, there is, again, the observational conditionals, right? I mean, what is now free energy given that, but just like perhaps molecules don't want to be round, right, or don't want to be flat, I mean, or don't want to be forced to be planar, and hence in our database, if we would just look at, okay, what is the free energy of flat molecules? Well, yeah, that is really just like coincidental, right? It's not necessarily causal. There's also the intervention joint. This is the distribution if we force molecules to be flat. I mean, and then these molecules, they might be unhappy, they might behave a bit differently. And then hence we have also the interventional conditional y given that we actually did this, right, to the poor molecules. Now the learning setup in causality is typically as follows. We have some data from the observable joint because we were too lazy or somehow barred from running the experiment, the interventional experiment, right? So we don't have this data. We don't have the data well, from here, we can't sample data from here, and hence we can't directly estimate this. But we do get data from here, from the observable joint. And what we would like to have is somehow an interventional model. So now y, x, perhaps I should have done do x here, I mean, that's, which approximate this one on the right. That's what we actually want. And the big question is this even possible? Or when is this possible? And this is again where this do operator, the dual calculus, and I'm just skimming over the details, I mean, that I can easily spend a whole lecture about it, all the fine-grained stuff, where it plays such an important role. What it also elucidates, and this is well, I've said this now a number of times, but this is the most important thing that I can teach you in this lecture, many most important things, is that causal learning is impossible, and really just impossible. It's not possible without assuming something about the causal process, at least causal learning from observational data, right? What does it mean? So here now in the bottom left corner, we have the stuff we already know, right? There's some observable joint, observable conditional. This was generated by some model. And this is the world generating this, right? I mean, now, the point is that if we want to do causal learning and we want to see, okay, what is the effect of a certain intervention of changing our model, we need to have a model in mind. we cannot reason about what would happen if we remove this edge by, for example, setting, let's say this is the planarity, right, of a molecule. And if we just let this molecule go about as it does, the planarity then affects this, and then this, and so on and so forth. Right now, by forcing the planarity to removing this edge here, taking a certain value, we might, let's say, remove the causal effect here. And the whole model changes. The world starts to behave differently, right? These molecules behave differently. Now, it is impossible to do this thought experiment, right, of seeing what would happen if I were to intervene if we don't have a model in mind to begin with. And that is something I will get back to in a second, right? But it's really there's impossibility theorems. I mean, you cannot extract causal dependencies by just pure statistical methods. That's what we're going to derive. I quickly look at the chat, and let's see if this is something that fits. Okay, yeah. So Max asked, okay, so what do I mean with if I force the molecule to be flat? So whether this means that there's several databases, or if I require sort of bias in the distribution. I mean that I really actively. So I mean, well, it's not really Maxwell's demon, but I mean, it's then Vreeken's demon. I mean, any molecule that I can think of, right? I mean, I just force it to be flat. I mean, it may want to do this. No, it's not allowed, right? I mean, that's and well, then otherwise with this flattened molecule, it may do whatever it likes. I run it through the simulator or through the codes and whatnot, and then from that simulator, from that code, I can get a database. But I'm thinking mostly in distributional terms, not at the database level yet, but really like, okay, if I would magically access every possible molecule, right, but I force it to be flat, right? Or I access every possible molecule that fits certain other conditions, like, okay, up till K gold atoms, blah, 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 right? But I force it to be flat, right? I don't just look at those that happen to come out flat, but no, I force every molecule to be flat. I hope that answers your question. Good. Now back to the main point here. We need to assume a causal model. We cannot just drag this from data because we first need the model to reason about the what if situation. What would happen if? Because if we have this model in mind and then we have to mutilate it, right? So we removed something. Maybe I should have removed even more. I don't know. I can then start to reason about, okay, what would the emulated, like the interventional joint, what would it look like? I mean, that's so what would this system generate in data? And then what would this data, from this data, I can now say, okay, what would be the intervention conditional, right? So what would be the y given do x? If I did this, right, that is now the do x here. But I needed to have these models in mind, or I need this model and then I do something on it. And if I now was lucky, or I don't know, and I'm just really good at what I do, then this causal model was not far off for the task at hand. And that means that the emulated intervention joint, after mutilating it, after intervening on it, roughly corresponds to the intervention joint if you were to flatten the molecule, right? And if that is the case, if these are approximately or absolutely equal, then the interventional conditional that we would get if we would really reason about all flattened molecules, okay, that fits then the interventional conditional that we have here. Kind of makes sense, right? Basically, what I'm saying is shit in, shit out. That is the shortest way. If we assume a stupid model that doesn't have anything to do with reality, nothing is going to come out. Nothing sensible. Now, where does this lead us? I mean, because in the end, the only thing that we really have is this observable joint, right? I mean, this is just all make-believe, and not all these things here on the right. Now, through the do calculus, which are essentially simple algebraic mathematical steps, I mean, that equate under certain conditions, conditional distributions and interventional distributions. There's a number of rules. I'm not going to show them even, but through the do calculus, we can see if we can go from this expression here through the assumptions that we made here, if we can go all the way back to the observable joint. So basically, we try to walk back from here all the way to here. And if we can, what does this mean? That we achieve an estimable formula for this quantity, so for the interventional distribution, just based in terms of things that we can actually observe. And if this is possible, and in many cases this is not, right? I mean, this is very unfortunate, but in many cases it's not, then we call this interventional distribution identifiable. Now, what is the main takeaway of this slide? I mean, we have to assume something. We cannot get away with it. If we don't have these pinkish boxes, there's no way for me to walk back to the observable joint. Just simply not. It always has to go through this model. It also means that it's the model that essentially defines whether this quantity is identifiable or not. If I make very relaxed assumptions like, well, anything could happen, I can almost guarantee you it will be impossible to achieve identifiability. You will not be able to really estimate what is the causal effect just from data you observed in the wild. If you make very strict assumptions about how the world works, which may be completely bogus, right? Okay, let's play pretend. That may allow me to very easily walk from the interventional conditional to the observable joint. And the name of the game in causal research these days, in the last decade, massive amount of progress has been made. Essentially from there was barely no bridge at all, just the observation, hey, we could perhaps build a bridge. Now for more and more settings, there are these bridges built. So this means that under certain models and the assumptions they come, we can actually estimate causal effects from just observational data. This is great. Now that's the good news. Now let me take a step back again, because I already mentioned a few times, impossible, impossible, impossible. And in the, I think it was published 2 years ago, the Book of Why by Mackenzie and Pearl, or Pearl and Mackenzie. So Judea Pearl is well, the great mind behind, like, I think all well, not all, many of the big breakthroughs in causal reasoning and causal inference in the last 2 or 3 decades. For that, he also won the ACM Turing Award, which is sort of the computer science Nobel Prize, you could say. And in this book, he and his co-authors, Min and Ron by Marjan Harel, introduced the ladder of causality. And this is a nice graphical depiction of lots of theoretical results that would make your eyes bleed if I show them. But I think this should be, in the next decade, this is going to be the starting point of many statistics lectures and many machine learning lectures. But right now, it's only halfway at the end of a course. So what is the ladder of causation? What is the ladder of causality? There are 3 steps. And each of these steps require a different set, an increasing set of assumptions about the world. So at the lowest rung, the seeing or the association rung, we can just deal directly with data we grab from the wild. And we don't essentially barely need to make any assumptions. I say barely because in many machine learning algorithms, we need to assume IIDness, right? I mean, identical independently distributedness, the basics. But that is all rung 1. We've given some observational data, we're good. And what can we answer? What are the types of questions that we can deal with? These are the what if I see, and particularly the seeing, not what if I do, but what if I see? And questions such as, okay, how are variables related? I mean, if I see a change in X, do I also see a change in Y? Maybe they're causally related, maybe they're not, but it's the seeing. So what does a symptom tell me about the disease? What does a survey tell about the election results? Standard machine learning stuff, standard stuff. All good, right? I'm not saying anything like, okay, boo, machine learning. No, this is the stuff that we can, and this is also why it works so well. This is all done. If you want to go to the second rung, you want to reason about doing, about interventions, like what would happen if I change the dial, right, the gauge on my coffee machine, or if I flatten these molecules, then all of a sudden you're out of luck. Rung 1, just plain data that you gathered, is not going to suffice anymore. We need to make assumptions about the causal model. I'm not going to go into the details like what is exactly the set, right? I mean, this has to do with this do calculus that I also don't want to explain to you right now. But we need to make assumptions about how we think the world works. We can't get away with that. And if we do make such assumptions, and especially if these assumptions are somewhat reasonable and fit the real world, then actually, if the model is identifiable, then all of a sudden, from the observational data, with the additional assumptions, we can answer questions. Okay, if I take aspirin, will my headache be cured? Right? Because obviously, I mean, people who have a headache take aspirin, so just associationally, you can't really solve this, right? I mean, that's basically, well, don't take an aspirin because then you don't have a headache. Or another stupid example and association level would be that in the emergency ward at the hospital, there's many people who don't make it, right? So if you want to maximize your chances for living, get the hell out of the emergency ward. That kind of foregoes the fact that you're not there completely voluntarily, right? And that, so you can only figure out by actively taking people out of the emergency ward that it was a really bad idea, so let's not do this. Okay, hence you need these assumptions about the world. There's also a third rung, counterfactuals. These are the more imaginative questions. So whereas in association, we just look at the data we have. In intervention, we, okay, what would happen if I change? And what would happen if I change? So basically it's forward-looking. And in counterfactuals, you reason about, okay, what would have been the case if I had changed, right? I mean, if I would have put on a blue shirt rather than a red shirt this morning, what would have happened? And this requires an additional set of assumptions, because now you don't just need to say, okay, well, how do I think that the world works? And I have all the initial conditions. And if I just make my molecule flat, what is going to happen now with it? But okay, what if I would have made my molecule flat 2 weeks ago? What would have happened in my system? Well, this flattened molecule would have had lots of effects downstream, and that makes many, many things much more difficult. That's the easiest way how I can explain it. Now, each of those rungs you can only reach by a certain minimal set of assumptions. It is impossible to do interventional things just based on observational data without assumptions. And no matter how hard you wish for it, and that's no matter how hard. So yesterday I came across a paper published at AAAI, which claims that they can do causal inference, determining whether X causes Y or Y causes X, purely about association with neural networks. It's bullshit. I don't know how this got through. It's absolute bullshit. I mean, it's a badly written paper, so I think the reviewers didn't pay too much attention. But it's really, it made my skin crawl. It's really, they claim something that it's just theoretically impossible. It's just the fact that they show that it works is that, well, perhaps they were lucky in which data they tested upon, or they're just trying to dupe us. But we know from theory, this is just simply impossible. You need to make these assumptions, and well, then we also need to make them clear. Okay, so much for the can we, or what is causation, and what can we do with it. Now I want to use the last 15, 20 minutes, whatnot, something like that, to explain to you how can we, given some data and a set of assumptions, how can we determine the causal network? How can we do causal discovery? So the idea is pretty much as I started in the lecture. We have these bunch of variates, right? I mean, descriptors, you can call them, different lingo, doesn't really matter. And what we want is we want to ideally have a fully oriented, fully directed graph over these, right? So the idea, just to re-explain it, if I tweak the value of Z, then Q and W are going to change, and Y and V is going to change because W changes, and because Q affected T also has some effect there, right? That is the general idea. How can we get this from just data alone? Well, we can't. We need to make some assumptions. Okay. Let me first give you a little bit of notation, or the name game, but let's identify which types of nodes do we have, such that I can explain what we're actually doing. My node of interest, special interest right now in the next 5 minutes, is T, node T for target, right? I mean, you could also call it Y, but let's call it T. Now, the parents of T in these graphical depictions are the ones that have arrows leading directly from them to T. So those are those. Then the descendants of T, those are the red ones here. You could also call them the children, but descendants is easier because that allows me to, in one go, also name everything that is, well, not a parent and not a descendant, or not a descendant, calling them not a descendant. Good. So now we have these three colors in that sense. Particularly the parents are important later on. So another thing that is important is that in this network, we have two types of variables aside, right? We have those variables that are determined by influences within the network, and within the network only. Those are the ones that I color now in darker blue, right? Those are the endogenous variables. We also have the yellow ones, the exogenous variables. They don't take any input from the outside, right? They could be like noise variables. I mean, it could be, I don't know, something that we might be able to intervene on. I mean, it could be like a temperature variable or some intrinsic noise. That's typically how people think about it. Good. Okay, now I need to lay more groundwork. I mean, I really struggled with laying out the next few slides in an interpretable manner. But well, I need to put quite a lot on the stack before we can explain everything in one smooth go. Suppose that we now that this actually is the true network that we want to discover, right? I mean, and we somehow, in using standard machine learning, we discovered that let's say, well, for example, Q and W, right? If we were to measure the values of Q and W, that they would be dependent. It is possible to predict the value of W better with knowing Q than, well, without knowing Q, because it shares some information through Z, right? So there would be an observed dependency there. It's not a causal dependency, but it's a dependency. Now, how can we reason about that? Back in 52, at the top of my head, 53, I mean, Hans Reichenbach, philosopher and partially mathematician, posited the principle of common cause. And this is really a cornerstone in statistics and causality. This really sort of was the building, that the stepping stone, the bridge towards all the things that followed. Basically what he said or observed is if two variates are dependent, right? So this would be, now I just call them X and Y, right? And that's, then if we measure this, right, and we measure this well, right, but, so not just over 2 or 3 data points, it may just be down to rotten luck, but we have a large enough database and we really see, okay, well, hey, wait a second, right? I mean, that's, let's say the planarity of the molecule and the free energy, they have something to do with each other. Then there's 3 options. Either the free energy causes the planarity, X causes Y, or the other way around, the free energy, what did I say? The planarity causes the free energy, would be then this one. Or perhaps there is something else, some factor Z, that actually causes both of them. There may still be a little bit of an edge in between, but that just mucks up the picture in that. And in theory, it doesn't matter. We can just rename the Z to be a super Z. And well, these are the 3 options. Now, the important thing to notice here, and this is where this principle of common cause really kicks in usefulness, is that if this is indeed the case, Z screens X and Y from each other. So that means that if I tell you the value of Z, then X and Y don't know anything more about each other than, well, just independent. They become independent, right? And that's, whereas in this case, telling you the value of Z doesn't give you any information about X or Y, and still Y gives a lot of information about X, and the same thing here, right? So, but only in this case, Z screens can reduce the effect there. It's very important, because that leads us to the causal Markov condition. And now we start to make some proper assumptions in that. We're going to be assuming that the world is Markovian, that it's possible to fit it in these probabilistic terms. So we have a distribution. I mean, first of all, we assume that there is a distribution, which may be rubbish. In many cases, let's say a social network, there is none, or at least not one that I can point at. But we have a distribution over our descriptors, our variates. And if we have a joint distribution from probability theory, we know that we can break this distribution up into smaller terms that make it more manageable to estimate and a bit more wieldy. And that's where Bayesian theory is all about. And there's also where the non-causal Markov condition comes down. How can we factorize it? And how can we factorize it minimally? What does it mean? This means that actually per xi, we can break this. So we can break this entire thing up as a product of smaller distributions that are just over xi, where we feed in, well, just the parents. So basically just the nodes that have an arrow outgoing towards the xi in question. Those are the only edges I need. Any of the other edges, they're not going to help me. I don't need them, right? Because I get all the information that I need just from my parents. And if we assume that the world works like this, there are some implications. I'm sweeping them under the carpet right now. It's a bit idealized, but this is not the worst set of assumptions to make. Now, what does this mean? I mean, if we combine what we see here, even if you don't draw it completely immediately, and Reichenbach that we saw before, this means, just to reiterate, that if we have some variable of interest x, and if y does not cause x, then this holds. So that means that predicting x with just the actual parents of x that do cause it, right, is going to be the same as predicting x with its parents and y. Or another way, or other words, or a way around, we can just simply remove y here and still achieve maximum information. We didn't lose anything by throwing out y. And that is the general gist of the algorithm I'm going to be sketching out in a few minutes. So we can weed out, start with a full graph, non-causal edges by trying to figure out what can we screen away. What information is indispensable and what information is just, we can just throw out without any loss. This allows us to identify under assumptions, faithfulness, sufficiency, I'll point out a few in a second, any non-causal edges, which is great. And we can even partially orient the graph that we then get up to Markov equivalence. Okay, what is that then? Well, Markov equivalence is that you cannot. So how should I say this? Actually, I should have introduced another slide. Yeah, let's actually go back to Reichenbach here. If I have this x and y, and I can find a z that makes them independent, so basically we are actually in this situation. Okay, great, right? I mean, that's essentially I needed a z to determine what is going on between x and y. That is the only case that I can actually do something sensible. In all other cases about three variables, x, y, and z, probability theory bites us in the back, just I had in my almost very first slide, where things become symmetric. So P of the joint distribution P x, y, P x, y, z, and the factorizations according to this diagram, they're all indistinguishable. So what does this mean? Here we have the four orientations that I can have over these three variables without having an explicit connection between x and z. Now we can reason about these. So what actually, let me first also explain in graphical notation, this means that, well, x clearly causes y, right? I mean, that I didn't need to explain, and y causes z. But there's no edge between x and z. This means that x and z are independent. Right? They're independent, but they are not. So what does that mean? So there is no direct effect from x to y or from x to z or z to x, right? I mean, this is why there's no edge. So in that sense, they're independent. However, they are dependent, if you just look at the values of x and the values of z, because x holds information about z through y. Right? Y may murk it up, right? This is some process, but because y takes information from x, z gets some information from x through y. Right? So what does it mean? For these three cases, x and z are, if you measure it from just observational data alone, they are dependent, written like this. But if you take out the y variable, so you condition on it, then all of a sudden, so basically that's, so you remove this y, and as a result also all the edges, then there is no connection from x to z or z to x anymore, and then they become independent. So that holds for these three cases. This means that these three cases we cannot tell apart. Nothing we can do. The good news is there's also one case at the bottom, which is not green, it's blue, and just one. So what do we have here? X and Z right now, so there's no causal link between them, that is good, but there's also no path from the one to the other. So there's no way that the information from X can actually reach Z because, well, it just accumulates in Y and that's that. Same thing for Z. So that means if we observationally measure X and Z, they're going to be independent, right? And they don't tell any information about each other. However, the moment I condition on the middle variable, just like I did here at the top, all of a sudden they become dependent because Y, well, that's the accumulator of the information from X and Z, right? It's a collider, as we call it. So this collider graph is the only out of these four, and also these are the four possible non-triangular shaped orientation we can have with three variables, we can identify uniquely. So these three, they form a Markov equivalence class. We can't tell them apart without additional assumptions, additional tricks. that I'm not going to go into. And the last one we can tell apart. Okay, so we now have two main ingredients. We have learned that we can weed out causal, non-causal edges by just seeing, okay, do they add any information? This goes thanks to Reichenbach. Can we screen things away? If we can screen them, okay, we don't need the edge in between anymore. Okay, good. And what we see here will allow us to partially orient some of the edges that we find left. One of the most well-known algorithms to determine such a causal network, which ultimately is, I would say, the most interpretable model that you can get, because it really tells you, okay, if you were to fiddle with this variable, then something's going to happen there, or well, not, because there's no path from A to B. The most well-known algorithm is the PC algorithm, named after Peter P. Spertus and Clark Limmer, both from CMU in the States. And it's a bit of a, well, a golden oldie in that. So it's from the late 90s, early 2000s. I mean, there are some different installments of it. It has been surpassed. I mean, you have more dedicated algorithms that do better in specific cases. But let's start with the basics, right? I mean, that's it's also, if you hold it right, it is the go-to algorithm. That, we also use it on a daily basis in my group. So what does it assume? I'm not going to go through everything, but I just wanted to list that it makes assumptions. It has to, otherwise it would not be at rung 2, right? Then it would be at rung 0 or 1 and it couldn't do anything. So the data generating distribution has the causal Markov property, or the causal Markov condition, I called it earlier. The distribution needs to be faithful to this graph. What does that mean? Well, in a nutshell, it means that if there's no edge in the real graph, then we are not that unlucky that in the data we sampled, all of a sudden there is an edge, and the other way around. So that's the faithfulness. So basically, if we see a dependency, it can be explained, right? There's either a direct causal edge or it can be screened. That is the core idea here. Every member of the population is the same distribution. Let's forget about that. All relevant variables are in G. It's a very important one. This is called causal sufficiency. Basically, what we're asked is to derive the network, the causal network between the descriptors we're given. But if you don't give me, let's say, the one descriptor that rules them all, yeah, you kind of are screwing me over, right? And there's no way I can recover the true causal network without knowing this sort of descriptor in the sky, right? It doesn't need to regulate everything, or even just parts, right? If I don't get it, my conclusions will be moot. This is a very strong assumption. Basically means that this algorithm will give you potentially bullshit answers if you haven't measured everything relevant. Okay, but we need to assume something, otherwise we're back to rung 1. Yeah, that's the only one graph I'm going to skip. Good. The algorithm, or how we use it in practice, there's 2 steps. First, we're going to use conditional independence test, Reichenbach, and the stuff that we saw, to determine the undirected graph, the skeleton. And then we're going to orient it. We're going to try to orient as many of the edges as we can. These 2 steps are common to almost all, and I say almost because we just proposed an algorithm that does it completely differently. Okay, that's my bad. This is basically how all causal algorithms work. So hence this is a good example. So how do we discover the skeleton? Let's do this because I realize that not all of you are computer scientists, or maybe none of you. So I'd rather explain this visually than in just in pure math or whatnot. This is the starting point. We start with the full network over the variables in question. And what we're going to do, we're going to iteratively remove edges. How are we going to do that? Well, we're going to use Reichenbach. Right? This means that if we see a dependency between 2 nodes, well, then either there is an edge or we can explain it away. But if we don't see a dependency between 2 nodes, then Reichenbach on the one hand, and faithfulness on the other, right? So we don't see dependencies that are not there, and we don't see independencies that shouldn't be there. That means we can also remove it. In other words, we start by just looking at every pair, xy, xz, qz, and so on and so forth. And if they are independent, and for that basically means you have independence tests, you can also say, okay, can you predict x from y or y from x? And if you can, they're dependent. And if you can't, they're independent. Of course, depending on your model again, okay? So this is how we start removing some of the edges. The algorithm looks like this, if you're so inclined. So just removing the individual, let's say the pairwise edges that are independent. Okay, that's a trivial step, right? I mean, that you could already see. But how about leveling up from there? And this screening that Reichenbach basically pointed out. Suppose that we're now interested in figuring out this edge between x and z, right? I mean, so we measured it, And yeah, there's really something there. There's really something there in that. So we can't just throw it away just like that, right? Suppose. Let's play pretend. Now, that means that we can't throw it out just yet, but we can try to see, can we screen it away? What happens if we now look at the dependency between x and z if we condition on y, right? So we now look at all the samples, all the possible values of y, and for each of those we see, okay, are x and z dependent or not, right? And it might be that all of a sudden they're not dependent anymore. Basically, all the information flowed really to y. Okay, this in this particular case is the case in that. So they become independent, and that means no causal edge. Thank you, Reichenbach, right? Okay, we keep on doing this for every edge that we see, right? So now that we've established that this edge is gone, right? We might now want to check, so these become now gray again. We now can see, okay, this x and y edge. Can we explain this away with, well, we don't have to check z anymore because z does not screen x and y because this edge is gone. But for example, x and y could be screened, could be explained away by w. Right? Okay, no, it doesn't do anything. Maybe by q, doesn't do anything. Maybe by t, doesn't do anything, and so on and so forth. Okay, well, we do this for every edge that we have and for then every node that is connected to both of them, every single one. This removes many edges. This sparsifies the graph very much. And in the next step, what we're going to do, after we've done this all with the conditioning for one variable, we're now going to look again at x and y, right? We want to remove this edge, see if we can do it. And just q by itself didn't do it. Well, now let's look at all pairs. Let's look at q and t at the same time, right? So both q and t are connected to both x and y. So perhaps together they can explain this edge. Well, in this particular case, no such luck, right? But some of these edges will be able to be explained this way, and hence we keep on rinse and repeat until we achieve the causal skeleton. We can't remove any further edges anymore. And this is the provably correct, if the assumptions that we set hold, provably correct answer to the question. We now have the causal skeleton. We don't have the directions yet. That's what we're going to do next. But this is going to be the correct skeleton. Let me just repeat, if your assumptions suck, then so is the network, right? If there's actually a variable j that actually causes x, y, and q, for example, then, or maybe actually mean y, t, and q, then maybe these edges are not there, right? Maybe this is actually secretly this j that we didn't observe, and hence the conclusion here may be moot. It may actually be that because these are now then explained away, we also don't need this one anymore because perhaps this one now, and so on and so forth, right? So the assumptions are really important. On the question, how well does this scale with the number of samples? Actually, so let me go back here. The more samples we have, the happier we are from a quality perspective. Because in the end, what we're doing, we're testing here these independences, right? And these independence tests, they're quite data hungry. And they become more and more hungry, exponentially so, the more variables you condition on. So the larger the set A becomes, right? So if this is empty, right? So we just test x and y, then tens of samples is going to be fine. If we now want to see, okay, x and y conditioned on q, well, okay, 100 samples is probably, depending on the test that you want to run, might be okay, but rather more. If we now want to test on q and t at the same time, well, you again need more. Why do we need more and more? Because essentially what we're doing, we're looking at x and y dependent or not, if q takes possible value 1, and possible value 2, and possible value 3, and so on and so forth. So we take all the data, we essentially split it into smaller and smaller parts, and for each part, so for let's say the value combination q takes value small q and t takes value small t, that may be just very few data points. And then estimating the independence of x and y over very few data points, that becomes statistically a very icky exercise, right? So the more samples, the better. That's on the quality side. Most independence tests scale reasonably well in the number of samples. Linear, log linear, maybe quadratic, but typically not much worse. But it's also a price you're willing to pay, or should be willing to pay. The thing, speaking of scalability, where you should be really very much worried about is the number of variables. Because clearly, if we have tons and tons, let's say, thousands, millions, or hundreds of thousands, whatever, of variables, we need to do many of these independence tests, right? I mean, before we have pruned away all these edges, I mean, my God, that's going to be a lot of work. The good news there at the same time is that, well, it's not actually the number of descriptors, the number of variables that bite us in the back. It is the density of the true network. Because if the true network is very sparse, that means that we can very quickly remove many edges by just straight independence tests or having very few conditionals, and we can sparsify the graph very quickly. But yeah, we don't know the original network to begin with, right? So your mileage may vary, as they say. Good. Now, the causal skeleton, let's try to orient it, and then I wrap up the lecture, then we're done. So for this, we're going to use this orientation, well, let's say this Markov Equivalence class thing that I discussed earlier, but we had the group of 3 possible orientations, right? So we take a group of nodes, let's say X, Y, and T, for example, right? And we see what happens if we now condition the dependence of X and T, right? And that's on Y. Are they still dependent? Yes or no? And if this now falls in the case that, well, there's an edge from X to Y and an edge from T to Y, and this collider case, and we're in this blue case, that would be great, because then they would be independent if we don't look at Y, and they would be then independent if we do look at Y, and we can uniquely identify, hey, these are the directions. If not, okay, too bad, we can't say anything. We do this for every triplet. So for every triplet like this, I mean, we do such a conditional test. And well, this is the rule 1, I mean, that so slightly different letters that I use here, I mean, not to muck up the matching to the actual graph here. And what we find in this particular case, this example, that Y, Q, and T, they have this collider structure, and the same thing for T, W, and V. So that means that these edges we can orient. There's a number of other orientation rules that you can, based on independence tests, you can prove that, yes, I mean, now we can really unambiguously tell it is indeed this causes that and not the other way around, because otherwise we would see something else. So we can prove, for example, if you have such a structure, I mean, that's, so if we know that A causes B, B causes C, we know that A and C are independent, well, then it is not possible, so after having first applied all these rules, that actually C causes B anymore, because then this would have picked it up. So this is sort of like a leftover, a waste bin type of orientation rule. So this means that in these structures, okay, B causes C. Similar for rule 3 and 4, that where I don't want to go into details. And this allows us, if we're lucky, to orient a large part, and in practice, typically only a small part of our causal graph. This is the state of the art until a few years back. Or actually, it's still been for many people the state of the art. I mean, but the part that I'm not going to be telling you about at all today, just for lack of time, let's look at the clock, is the fact that actually with some, I would say even mild additional assumptions about how the world works, sort of inspired from Occam's razor, I mean, that's simpler is better. It actually turns out that, so in this particular case, we would not be able to orient this edge, but with a few additional assumptions, we now have really, really well-performing methods that can orient even just simple pairs. We have methods that can do so even if we haven't measured this J that might or might not actually influence X and Y. It can determine it automatically. Like, okay, well, hey, this looks icky. Probably there's something going on with very high accuracy. We can discover such networks with this secret J that may be mucking up things. That, well, to explain those, I would need at least another full lecture, so that I'm going to just only allude at, hint at. But with what you've seen today, you at least know what is possible, what is not possible. You know the basics. You know what an interventional distribution is. That is really important, and that's because that's the building block for all of statistics that follows. And that all that you knew so far were basically, well, you got taught the advanced stuff before the basic stuff, and that screws up thinking a little bit. You know that certain things are simply impossible. Very important, very important. So you don't have to try. You don't have to try even. And what I explained is this constraint-based causal discovery, this PC algorithm. So golden oldie from, I think, 96. There are improved algorithms that are faster, that are better in certain ways. But it is a basic algorithm that helps you to understand, I mean, what we can and what we can't do. And especially, that's why I put this again, remember the ladder. It is impossible to reach Rung 2 performance without assumptions that allow you to climb to Rung 2. It is impossible to do counterfactual reasoning without the proper assumptions. So a deep net that you just learn plain on data is never going to be able to do interventional or counterfactual reasoning. It can't, right? And if you're okay with that, because you just want to predict why, because I mean, x1, 2, 3, and z1, 2, 3 you can measure, perfect, absolutely perfect. If you do want to really reason about what causes what, okay, then we need a new class of deep neural networks or other methods. So after all, even with all these assumptions, I mean, that the golden rule, as Pearl put it, is that a causal claim you simply cannot establish by pure statistics, just by looking at data. I mean, that you need these assumptions, and well, these assumptions ideally need to be verifiable, and we don't really know if they hold, right? So the golden standard is really this randomized controlled trial, and that, by really actually doing this experiment, right? And that by really simulating all these flattened molecules in C and stuff. By, of course, I mean, there's an assumption there. I mean, how good is your simulator? How good is your code, right? And that's, of course, the FHI code is the best, but I hear that at Humboldt, they also have pretty good codes. And well, I'm going to leave that discussion to you. Good. So with that, I want to wrap up. Thank you very much for your attention. I'll happily answer any questions. And that I hope that you learned something. I hope that I didn't disappoint you too much by saying too often things are not possible. Because personally, I think that knowing what you can't do really sharpens this thinking about, okay, so how can we make that actually true? I mean, how can we either circumvent that? What do we need to do? What can't we do? Good. Let me have a look at the questions asked in the chat. I mean, you're also very welcome to ask them by turning on your camera. And that, but I'll look at Max's question. Let's see. Yes. Okay. That's a good and very nice question. Yes. That. Let me go back. Let me actually go back all the way here. So this graph.
Sorry, could you please read the questions out loud for the recording?
No. So what I'm going to do, I'm going to direct, because well, I can read it, but I think I can rephrase it better. But for that,
okay, thank you.
I first need the diagram here to directly go to the main point. So I've been using this graph here as sort of a mental image of how causality may happen in our head, right? I mean, that's this is a very limited depiction of what happens. So if this diagram is the only thing that we're only after determining does X cause Y, yes or no, and yes, then there's an edge, right? And yes, there's nothing else causes Y, right, or X, right? I mean, X is really exogenous, and this is the conclusion we're going to draw. This diagram is perfect. And the exercise that we saw, be it through the PC algorithm, it's perfect. However, if somehow we want to determine how strong is this edge, or is there a hierarchy? So let's say between, so here we have multiple edges in common. This edge is more important than that one. And perhaps there is actually also an edge here. Let's play pretend Z. The Z to T edge, that's the least important, right? And that's that was the rephrased question. I mean, that's can we get more out of this diagram? And the answer is yes, but also no. I mean, this diagram by itself, so a plain acyclic directed graph, oriented in this particular case, it basically just gives you the general overview. And the PC algorithm just tells you, are there edges and what are the directions, or at least some of them. Now, after you have obtained this through the PC algorithm, what we can, of course, do is all sorts of nice other exercises, downstream exercises. So because if we now know that, hey, X and Y, right, I mean, we can try to see, okay, well, how much better can we predict Y if we use X or not, right? And that's and the definition like that, we can formalize this in a much more neater way, that gives us essentially a weight, strength of this edge, right? I mean, that's, let's say X is almost indispensable of Y, right? I mean, Y is almost a copy of X. It's a very strong edge, right? I mean, that's same thing here. We know that we need, if our assumptions hold, let me just repeat it once more time, we need both Y and Q. Okay, great, but let's just see how well can we predict T if we only give it Y, respectively only Q. Well, with those two quantities and the quantity how well can we predict t given both y and q, we can put this together, one and one together, and say, okay, well, hey, if we lose y, we lose so much information, right? Maybe we can predict t so much worse. Okay, this is a pretty fat hedge, right? And that's and this is a really thin one, and well, and so on and so forth. So that allows us to guesstimate what are the let's say the strengths of these edges, and gives us an easy way of building a hierarchy. Now, if you want to don't guesstimate this, but get the actual causal strength of this edge, well, then we need to go back to theory and see, is this quantity actually identifiable based on the assumption that you make? And under the basic assumption that PC algorithms make, that's not going to happen. That's not going to happen, right? I mean, that's those assumptions are essentially too weak to draw such strong conclusions. So what the name of the game is in causal inference, so where a large part of my group is working on, is essentially trying to find the smallest set, the weakest set of assumptions, such that we can provably achieve a certain goal. Exactly like Max just asked me, okay, how can we determine the hierarchy or the strengths of these edges? So of course, if we assume that's well, there's 3 moons and grass is blue and Easter and Pentecost fall on the same day, sure, then I can determine the edge weights. That's useless in practice, right? So the name of the game really goes through this diagram that I showed here. Let me just quickly show it again. Up. This is in a way the cornerstone of causal inference. I mean, what is estimable, what is identifiable, under what assumptions? Good. I hope that answers the question. I hope it was also clear enough for the rest of the audience. Okay, another question by Tim. Yeah, okay, that's a good question. That's let me go to the right slide. Oop, where are we? Yes. So the question is, does the PC algorithm have any, let's say, special ingredients that avoid it from creating a cycle, right? So, and the problem with cycles is that, well, I mean, the theory breaks in a very ugly way, but also even mentally, right? I mean, if Z causes Q and Q causes T and T causes V and V causes W and W causes Z again, then, well, you have a feedback loop, and by just a single snapshot of your data, one observation at one instance of time, you can't determine this at all, right? So cycles are only detectable if you really have temporal observations, and all this theory kind of avoids that a little bit. We can extend it, but we avoid it. So back to the question, how does it avoid cycles? Well, basically with a very cheap trick. I mean, the cheap trick is that we define the goal being, or basically we define where is it? Where are we? Yeah. It has the causal Markov property. And if I now go back to the causal Markov property, where are we? Here, that's the Markov condition. This thing over here, implicitly under the hood already says, okay, I mean, no cycles allowed. It has to be a factorization of this thing, no cycles allowed. Okay, so that is one way, but there's also another way how you can see that it actually doesn't allow for cycles. I mean, that's perhaps even cheaper than just not allowing it. In that, it finds a causal skeleton. It finds an undirected graph, and well, in an undirected graph, well, there's no cycle as such, right? I mean, well, there's this loop thing here, but we don't know the direction. So is it a cycle or not? Well, we define it not to be a cycle because we want a directed acyclic graph, right? A DAG. And the rules that we have, the orientation rules, they make use of this requirement of acyclicity. So this first rule, not yet, right? I mean, that's the first rule is really all about the colliderness, right? I mean, this one special case that we saw. Then the second rule, same thing. But now the third rule over here, right, which we then add additional edges, and it's the one that I skipped in the interest of time, but now we can go over time, that's good. The rule essentially says, because we have now here A causes C, C causes B, this one is undirected, but we do not, I'm slamming my fist on the, oops, my microphone is slamming my fist on the desk, because we do not allow for cycles, it is not allowed that B causes A. That's our assumption of the world. And because we don't allow this direction, well, there's only one other option left, And that means that we orient A to B. Ta-da, done, right? A similar line of reasoning is the case here for rule 4. That one is a bit more involved. So you could say that there's, well, it's basically by definition, it is because it essentially does not find these directed networks directly, but it finds these skeletons, which are not cyclic at all. And then the orientation rules, they again make use of the acyclicity. And altogether, be careful what you ask for, right? I mean, that's, or you get what you ask, but you always should be careful what you ask for. I hope that answers the question too. Yeah, well, this perhaps actually means, well, sometimes, I mean, so good questions make you feel stupid. And that's, so Hans just asked a very good question. Could I point out a good resource for further reading? Yeah, well, now I just realized that I didn't, I mean, I mentioned the title of a book. I mean, that is something. I would most strongly recommend, out of all literature there is, I mean, 2 books. Let me actually just go to the conclusion slide. I mean, that's that we don't have this on the screen anymore. There is the first one that I recommend is the most technical popular science book that I've ever read, which is The Book of Why, which I already mentioned the title of. So Mackenzie and Pearl and Mackenzie, I've forgotten which order it is, the authors are. And this is Pearl's, I would even say, attempt. I mean, it's worked out quite well to write an easily accessible text introducing people to the notions of causality and, well, let's say the problems that causal inference has faced within statistics, and why are we only where we are and not much further, and all that. What is possible, what is not. Very accessible, very accessible. But if you don't know the basics of statistics, right, so if you had trouble following this lecture, that book may already be too technical, because he kind of assumes a lot of his reader. So I can also mention a book that I don't recommend to anybody, but at the same time, it's the best book on causality, which is called Causality, written by Judea Pearl. I think the original edition is from 2001, updated in 2009, maybe an even newer version. It is one of those books where the learning curve is a step function. So when you start reading it, it's all gobbledygook, and it's like, what the hell, right? I mean, that's, as I like to say, it makes my eyes bleed. Until at one moment it clicks, and then it's like, yeah, this is the cleanest way to explain things. I say clean, I don't say best, because the introductory value of this text is very low. And there a lot of background is required from statistics. So Causality is really a book that at best you read after Book of Why, but probably only if you really want to dive deep into this field. So that is not a recommendation, right? And I said I wanted to recommend 2 books. So there's one other book that I do like very much, because didactically it's a much better text. However, let's say the scope of it is much more constrained. Maybe those two have something to do with each other, which is the book Elements of Causal Inference by Jonas Peters, Dominic Jansing, and Bernard Schellkopf, of which Bernard Schellkopf is also a director at the MPI in Tübingen. Dominic Jansing used to be a senior researcher there, and Jonas Peters did partially his PhD there. So you can kind of see where the root of all evil, right? And this is a book, it focuses not exclusively, but mostly on this case that I did not get to discuss today, namely the question, if we have only 2 variables, let me quickly dig up the right slide. Where's Reichenbach? Where are you? Here. Suppose that we found that X and Y are dependent, and we didn't measure, or we don't know, or we can't really think of any Z that might screen them. So this is not an option, this is gone. Then it's either this one or that one. How can we tell those apart? And well, it is a very good story on how we can actually do so. And that book goes through these motions in a very clear fashion, while also explaining many other basic things. So it's more technical than Book of Why, way less technical than Causality. And I think those 3 together form a very good gamut. So I can also, I don't know if there is a website or some channel which I can share this easily, but I can write the titles to the organizers of the lecture series, and then they can distribute it further if this is desired. If there's any other questions, I mean, feel free to reach out by email. I'm not perhaps the world's worst email user, It may take a little while to answer because I'm also busy with a number of things, but I promise you will get your answer in due time. So don't be shy. Good. Well, on that, if there's not any further questions, and it doesn't seem to be, let me say once again, thank you very much for your attention. I hope that right now this will set you on your path to thinking about causality differently. And well, the link to interpretability I didn't really get to, but I think it's kind of obvious, right? I mean, that's interpretability is the effect of cause, of causality. Good. Okie doke. Bye bye.
Bye.
All right, thank you.